Good afternoon, all. Today we will start with the unit 3, which is a recurring neural networks. It belongs to the deep learning syllabus of BERT. So before going for this recurring neural network, let's have the a little recap of what we have done in the previous units and what was there before the recurrent networks, right? So let's move ahead, and this was our agenda. First, we'll see, and then look towards what is feed forward network versus the recurrent network. So to begin with, I would like to say that to understand why recurrent neural network exists at all, first, we need to be completely clear about how a feed-forward neural network processes information. So, in a FFNN network, data enters through the input layer, passes through one or more hidden layers, and exists through the output layer. So, always moving in a single direction from input towards output with no loops or backward connection within a single path. So this is how my feed forward neural network works. There is no backward loops. There is just one-sided information flow, or and one-sided calculations are done, and then input it forwarded to the next stage. So every prediction the network makes is based only on the current input. The network has absolutely no way of knowing what input it processed a moment ago because it has no internal mechanism for storing that information, right? Think of it like a person answering a series of unrelated multiple choice questions, where after answering each question, they are made to forget it completely before seeing the next one. So this works perfectly well for the task where each data point genuinely stands alone. For example, classifying whether a single photograph shows a cat or a dog, or predicting the house prices from a fixed set of features like area, location, and number of bedrooms. So in these both cases, the order in which you feed the example to the network doesn't matter. So each input is completely fixed sized, self-contained unit of information. So in these scenarios, the feed forward network works perfectly. Correct. Moving ahead, let's go ahead and see like why we say that it has no memory. I have already told you that there is no memory for this feed forward network. Now the problem arises the moment data becomes sequential, meaning the meaning or the correct interpretation of the current atom depends on what came before it. Language is clearest example of it. So consider the sentence, the cloud are in dot dash dash dash. Example, right? What does this example say? That a human or a good model can predict the word sky, right? Because it remembers and uses the words that came before. Now, consider trying to do this with the feed forward neural network. Now, you would have to feed in the clouds, are, in, the as one input. But the network has no built in concept of a sequence or the order dependency. It would need the entire sentence stuffed into a fixed sized input vector. And it would treat that vector no differently than any unrelated set of numbers. So, with no explicit understanding that word three came after word two, right? So, the word sentences are not all the same length, but the feed forward neural networks required a fixed size input. So, there is no natural way to feed a 5 word sentence and a 50-word sentence into the same network without awkward padding or the truncation. This is a precisely the gap that recurrent neural networks were designed to fill. So again, as a conclusion line, what we would like to say is recurrent neural network solves this by introducing a feedback loop. The network maintains a hidden state. Think of it as the network short-term memory, which gets updated at every time step and is passed forward to influence the processing of the next input. So concretely, when an RNN processes a sentence word by word, at each time a step T, it takes two things as an input: the current word xt and the hidden state h minor h, this base to the t minus 1. That summarizes everything the network has seen so far. So it combines these to produce a new hidden state, which is my ht, which then gets passed along to the next time step. So again, as a concluding line, what I would like to say is this: RNN has two inputs at a time. The first one is the current word, which is my xt, and the next one is the hidden state, which is my h of t minus 1, which has the summarization of everything the network has seen so far. So it combines these two to produce a new hidden state, which is my ht, which then gets passed along to the next time step. So this is why RNNs are drawn with a small loop arrow feeding the hidden layer back into itself. That loop is the memory mechanism. Now, crucially, the same set of weights is reused at every single time step. This is called the weight sharing. The network is not learning a different set of rules for one word, word 1 versus word 50. It applies the identical transformation repeatedly, which is also why an RNN can handle these sequences of any length with a fixed number of parameters, unlike an feed forward network, which would need a completely different, larger architecture for the longer inputs. Right? So, a simple example I would like to say for this is: imagine reading the sentence, I grew up in France and I speak fluent French, word by word. Now, as you read each word, you are not starting from the blank memory. You are carrying forward your understanding of sentence so far. So by the time you reach fluent, your mental hidden state already contains the fact that the sentence is about the France, which is what lets you correctly predict the word. Next word is French and not a Spanish. So a feed forward network reading this word by word would have no such carried forward context. So the RNN hidden state is explicitly built to preserve exactly this kind of running context. I hope you have understood where does the difference of this feed forward network and recurrent neural network lies. So recurrent neural network has the memory. It has the hidden state, which preserve the information about the summary of the previous state, and which will help us to predict the information of the next state. Now, moving ahead to the next slide, we'll see the architecture of this RNN network. So, moving to this architecture, so here xt is the input at a time t, ht is the hidden state, a memory at a time t, and w represents the weight matrices, which stay the same across all the time steps, right? So the so now we will see about. I hope this is clear. We have already came across this about how it saves. Now we'll see the comparison of feed forward network versus the recurrent network. So here the data flows in one direction only in the feed forward network. In recurrent neural network, it has the loop backs, so recurrent correction connections. Then the memory of past inputs is not available for the feed forward network as we have seen till now. And the recurrent neural network has the memory, which is the hidden state. There is a fixed input size in the feed forward network. In the variable, but in the recurrent neural network, we have the variable length sequences. There is no parameter sharing, which is available in feed forward network. Now, the recurrent neural network has the same weights every step. Feed forward network is best suited for the images and tabular data. The recurrent neural network is suitable for the text, speech, time series, and videos. The training is the standard backpropagation in feed forward neural network, and the recurrent neural network has a training in a backpropagation through the time, that is BPTT, which is the term for the training of the recurrent neural network. Right? I hope till here you are clear with the difference between the feed forward network and the recurrent neural network. Right? And so we will move to the types of this RNA. So let's move ahead to the types of key terms. First, we'll see the key terms. These key terms are neuron. So like we have few terms which we have used till now. So these key terms we will be looking as the neuron, which is unit, which is a single computational node which multiplies the input by learned weights, adds slices, and passes the result through the activation function. We have already seen this. Then there is a layer. Layer is a group of neurons that all receive the same input and produce their output together. Then we have the weight, a learned number representing how much importance to give a particular input. So higher the weight, more the influence. Then we have the bias, an extra learnable number added to the neuron's calculation, letting the network shift into its output regardless of input. There is an activation function, a function which is tan H sigmoid ReLU applied to a neuron's output to introduce the nonlinearity, enabling the complex pattern learning. Then we have the hidden state, network's working memory at a time step, vector summarizing everything relevant processed to so far. Moving ahead, we'll see the types of the recurrent neural network, where we classify the RNN by the shape of their inputs and the output sequences. So here we are able to see the five configurations or the five types of the recurrent neural network. So RNNs are commonly classified by their shape of their input and output. So that is how many times atoms go in and how many come out, and whether they are aligned step by step. So understanding these categories helps a student immediately recognize which architecture to reach for when a given real problem. And so look, we'll see this one by one in detail in the next upcoming slide. So here we are at least able to see that these types are one-to-one, one-to-many, many-to-one. Then we have many-to-many, and then many-to-many unaligned. Right. So the one-to-one is the example for the image classification. One-to-many is image captioning. Many-to-one is a sentiment analysis. Many is POS tagging, and then many-to-many unaligned is the machine translation, which is where it is used. Now look one by one. So first we have one-to-one and one-to-many. Right. So let's go into this. One-to-one is the simplest and frankly a degenerate case. Right. A single input produces a single output and with no real sequence evolved at all. So this is architecturally identical to the standard feed-forward network, and it's included in the RNN taxonomy, mostly for the completeness, or students understand it as the baseline from which the other types deviate. A typical example would be basic image classification, where one image in gives one label out. Fine. Then there is another type which is many to one. So one to many. Sorry, the another type is one to many. So it takes a single fixed input and produces a sequence of outputs. The classic textbook example is the image captioning. You feed in one image and the network generates a sequence of words as the output of dog, catching, frisbee, like this. So here there is exactly one input at the very first time step, and the network then generates the outputs one at a time. So typically using its own previous output as a part of the input for generating the next word, continuing until it produces an end of the sentence signal. So this was about the one-to-one and one-to-many type of the RNN network. I hope you are able to see this, the image captioning pipeline and how it is generating the one word at a, from a image, how it is generating the multiple words. That is a sequence of words in a given cycle. Then we have many to many and many to many, many to one and many to many aligned. Fine. So let's look at what does this many to one say. Okay. So many to one takes a full sequence as an input, but produces just a single output at the end. Again, this is extremely common in a practice. The clearest example is the sentiment analysis. Given the sentence, this movie was absolutely wonderful and moving. So with this sentence, the network reads the entire sequence of the words at a time, updating its hidden state along the way. And the only at very last time step does it output a single label, which is said as the positive. I hope you understood this many to one. So again, I will tell you. See, I have the sentence, which is this movie was absolutely wonderful and movie. So this complete sentence is taken by the network, updating its hidden state along the way. And at the last, it produces only a single label, which label is called as the positive. Right. So other example includes the spam email detection and the topic classification of the document. So these are the examples of many to one. Then we have many to many with aligned. So in many to many aligned produces one output for every single input. So with outputs generated in the log step with the inputs at the same time step. So the standard examples is part of speech tagging. Given the sentence, dogs run fast, the network outputs a tag for each word as it reads it. So dogs is my noun, then I have run as the verb and the fast as the adverb. So that's my the part of speech tagging. So for every token or every word, I get the output over here. So with the input length exactly equal to the output length and no delay between the reading a word and tagging it. So this is how my many to many aligned work. Correct? Now moving ahead to the last type, which is my many to many unaligned. Fine. And then of course there is a problem in that. So we'll see it in a detail. So when I have many to many unaligned, it is a trickiest and most practical important case. The input and the output are both sequences, but they may have the different lengths. And there is no direct one-to-one correspondence between input position and output position. Fine. Again, I will repeat the input and output are both sequences. Fine. But in this case, they may have the different lengths, and there is no direct one-to-one correspondence between input position and output position. So the textbook example is a machine translation, the English sentence. What does it say is I am going to market. Fine. So let me repeat it again. There is a statement which says that I am going to market. Now to the analysis, we can say that, okay, there are 6 words in the statements, correct? I am going to the market. So 6 words are there. So it might translate into Hindi sentence as मैं बाजार जा रहा हूँ. Now, if you count this मैं बाजार जा रहा हूँ, there are 5 words. Correct? मैं बाजार जा रहा हूँ. So 5 words are there. And there is no sense in which word 3 of the input maps to the word 3 of the output. I hope you have understood many to many unaligned problem. So where my input and output positions are different and there is no direct mapping and there is no one mapping of every word to word. Correct. So the whole sentence structure can reorder. So the simple RNNs, that is simple recurrent neural networks, which produces outputs in sync with the inputs, has no clean way to handle this mismatch. Right? So this is the exact motivation or this is the exact limitation which motivates us for the encoder decoder architecture. Right. So with this multiple types of RNN networks, we will be now moving to the encoder decoder architecture hereafter. Right. Any doubts till now? Hello, students. There is there any doubt till now?